Well, what a pleasure to be here. I have a feeling that this is a very profound time of transition for this discipline, this specialization of configuration management. And I want to start out with a joke that was very funny in the 90s when I was growing up. And it was a joke about the 70s in technology. And the joke went something like this. A chap had heard that computers would make his business more successful. He had sort of like an auto parts shop. So he went and found a bright person who knew something about computers and asked him to write some software to help with his business, stock tracking or something. And this guy came very well recommended. And every week, chap would call up the computer guy and ask, how's it going? And every week it would be, it's great. Everything's coming along brilliantly. Send a check. And so the next week he'd call, how's it going? Oh, it's great. Everything's coming along brilliantly. Send a check. And eventually the parts manufacturer, auto trader, whatever, said, okay, look, just tell me what you're actually doing. And the guy said, no, well, I'm pretty much finished writing the compiler, and I'm about to get started on the database. And that was funny in the 90s because we realized what an enormously unproductive time we'd all had in the 70s, with everybody essentially writing compilers so that they could write databases so that they could get on and write applications. And we don't do that anymore, In a sense, even the most intensely professional of our software professionals have stopped writing software. And so I kind of want to start with a provocative thought that for us to reach the next level, we have to be willing to stop doing things that we think are profoundly important to what we do every day. That software computer guy thought that writing compilers was what you did, right? The same guy, 20 years later, would be spending a lot less time writing compilers. So today I want to talk a little bit about application modeling, the magic of application modeling. But it does come with a little bit of a sting, this talk, right? Because in order for us, in that Zen sort of way, to reach the next level, we have to stop doing configuration management. Now, that's deliberately provocative. And in the same way that today I still write software, I just don't write the compilers to write the software, right? We're always still going to be doing configuration management. But we have to start to think about what we want to not do and what we want to do differently. In the world of software, right, I have three choices. I can sudo apt-get, or I can go to GitHub and then I can configure make and sudo make install, or I can fire up my editor of choice and start coding, right? And all of those are valid options, but there is a cost to doing the second two, right? I reckon you're about 10 times as productive using packaged software than you are if you're building stuff and installing it from scratch. And think of all of the inefficiencies that come there. You take responsibility for making sure that integration works. You take responsibility for making sure that security is done properly. You take responsibility for a huge number of things that otherwise you'd be sharing with package maintainers from Debian and Ubuntu. But that's okay. Sometimes configure, make, install. And occasionally write the code yourself, right? But you're probably 100 times more productive fetching stuff off GitHub that already does what you need than rewriting that from scratch, right? So we know about these choices. We're comfortable with these choices. We make smart choices in this world today for software. But what about for configuration management? See, what happens is things in life go from being scarce to being abundant. And there's a whole reason why that's the case. I grew up in a time when software was scarce. I remember reading about software in magazines, software that I couldn't get. And I couldn't get it because I grew up in a little town in the far end of Africa, and software came in boxes, and the boxes didn't all make it to the far end of Africa. But also I grew up poor. And I remember saving for 6 months to buy a copy of Smalltalk, right? So 6 months to buy a copy of Smalltalk. Think how the world has changed, right? We've gone from a time when it was the software itself that was scarce and expensive to a time when software itself is actually completely pervasive and largely free, right? And what happens as things move from scarcity to abundance is that we have to change the way we manage those things. Think of music, right? It used to be that music was scarce. It came on fragile media. And then it went digital and it started to become much more of a commodity. And then the internet came along, and most of us went through a phase of carrying around that extra little disk, right? The one that had maybe a couple of gigabytes or tens of gigabytes or terabytes of music. Because software was scarce, when it suddenly became available, it was very tempting to sort of hoard it. Now, we don't do that, right? Now we sign up to some sort of streaming service, and we essentially have all the music that's ever been created at our fingertips. So the problem becomes much more, how do we manage all of that music? Not having it, but choosing it, finding it, curating it. That becomes the problem. So this shift from scarcity to abundance is a really interesting thing. As far as software goes, we're also entering a profoundly different time. Not only is software pervasive and abundant, it's also become big. This is the age, not of big data, but big software, right? So what do I mean by that? Well, stick your hands up if you could probably, without really having to refer to many books or manuals or documentation, probably make your way through the configuration of a bunch of Linux systems, / etc., and Apache, MySQL. Come on. Yep, everyone's doing great so far. All right, excellent. Wait, keep your hands up, keep your hands up, keep your hands up. All right. This is the unicorn test. All right, keep your hands up if that same day, without really having to go and refer to a bunch of documentation, you could make it through a complete from scratch OpenStack install. But wait. So some people still got their hands up. All right, let's see. Stand up. Those of you who got your hands up. Yeah, no, seriously, stand up. Okay. All right, stay standing if you could make it through a complete Kubernetes install. Huh? Weekend. Ugh. You're hired. Right, Kubernetes and great. What about big data? Hadoop. Right? So what's scarce today? Is it the software? All of those things, free software, GitHub, go mad, go get it, right? There's no barrier to acquisition of software. What's scarce? Time, but more importantly, knowledge, right? Knowledge. And our tools, our configuration management tools, were born in an era where knowledge was not the constraint, right? Everybody knew everything about everything. So you knew exactly what you wanted to put in all of these configuration files to get stuff done, right? And like that frog in the pot of water that's slowly been cooked, the scale of software has risen without us really realizing it. And so what's happening is that suddenly these tools are failing us. And it's not to do with the tools. It's to do with the basic idea that these tools are designed to let you take knowledge about what's supposed to be in all these configuration files and put it onto ever-increasing numbers of machines. So we're going to have to change. We're going to change. And in a sense, we're going to change, but we're going to retain the benefits of everything we've got, right? The skills are not wasted. The tools are not wasted, but we're going to have to create new kinds of abstraction. So this is what's going on, right? It used to be that an app was like say a front end and a back end, a data store of some sort. And if you were lucky, then you scaled that out over like 4 machines so that it was highly available. And today, suddenly, we've got these topologies of software. OpenStack is many pieces of software. And those many pieces of software are not deployed on 2 machines or 4 machines, but on hundreds of machines. And I saw somebody, the founder of one of the configuration management tools, answer a simple question. They were asked, why is everybody failing to deploy OpenStack with this tool? And they said, oh, that's because OpenStack is the most difficult piece of software you are ever in your career ever going to have to deploy. And I beg to differ. OpenStack is just the first of the big software that we're all going to have to deploy. All the interesting stuff is about finding tens of pieces of software and spreading them out over hundreds of machines. How are we going to do that is the question of the day. Would you like an AI in your basement? Sure you would, right? To do that, you're going to have to deal with big software. PaaS, all of the new Docapocalypse things are big software, right? And we want them all. Now, we do have an answer for this. It's called SaaS, right? If you think about it, when your organization goes and consumes Elastic MapReduce, how much of your organization's time is going into configuration management for big data software? None, right? You've essentially outsourced the operations, the ops, to somebody else's team. And that's okay. That sometimes makes sense. But that is essentially proprietary. You're never going to get that solution on another cloud, right? And so we have a different kind of lock-in, but it's lock-in nonetheless. Now, in the same way that free software was a response to the scarcity of software, right? What we need to do today is to think about how we can move to reusable and open source operations, right? So that we can consume and reuse and share and crowdsource operations in the same way that we crowdsource software. Now, to do that, that requires encapsulation. Think about it. With the simple command apt-get x, I can get x. And it doesn't matter to me. In fact, I may be completely unaware what language x was written in. Every day, I'm using software that was written in C++. I hate C++, right? But I use it every day in the sense that I can just apt-get software. Haskell, JavaScript, Node, Go, Python, you name it. Apt-get encapsulates whatever it took to make that software work and bring it to a machine or remove it from a machine, right? And so there's an encapsulation story. We're not rewriting all the software into a new language to do this. We're just encapsulating software. Encapsulation also requires a model, right? In a sense, I give something up when I decide to apt-get software. And I remember a time when people were anxious about that. I give up the fact that, I'm optimizing it for a very specific use case or environment. But often, getting it fast and getting it done to a very high standard makes that a perfectly reasonable trade to make, right? So encapsulation requires a model. Encapsulation is critical for reuse. So if we were to go and look at how we could create reusable open source operations, what would we need to do? We need to figure out what we're going to model, right? So let's start with thinking about how people think about software, right? It's basically stuff connected to other stuff, right? And you can see this sort of picture anytime you go walking around a place that has whiteboards and developers, right? Or system administrators. Does this actually reflect configuration files or even machines? No, it doesn't, right? Some of those things may be on the same machine, some may be on many machines, some may be on similar machines, some may be on very different machines. Effectively, we're abstracting all of that into a model. And that's where we started with Juju. We started out by saying, let's see if we can enable startups in San Francisco working on Amazon to share each other's operations so that they don't spend as much of that angel funding Series A check on their own set of chef scripts for Hadoop or their own set of Ansible playbooks for something else, right? That they can reuse one another's work. And that's evolved. Today, it looks a bit like this. Now, this is a very simple example, right? I've got Memcache talking to MediaWiki, talking to MySQL with HAProxy in front of it. Once I move to a modeling world, I can do fun stuff, like I can say, well, maybe I want to use Galera instead of MySQL. So Galera will give me active-active MySQL. And if those two components, reusable components, speak the same language effectively, I could just swap them into the model. So I move to a modeling-based approach, and as part of that model, I gain the ability to substitute components. Now, this is a classic accelerator in technology. Once I can essentially isolate a piece and get people to work together to make that piece better and better and better without my involvement, right? Because they're also reusing it, everything goes much faster. And in addition, I gain the ability to swap out pieces, which means I can try forks of MySQL very, very easily without having to rework all of my own tooling, right? So moving to a model is really interesting. So I want to talk a little bit about the modeling language, because I'm willing to bet that everyone's going to figure this out. We figured this out first because we were looking very deeply at what people were doing when they were under pressure to do stuff faster and at scale. But everybody's going to come to this. So hopefully the language that we use to describe this stuff can become common, just like we talk about objects, just like we talk about classes, just like we talk about other constructs in software development. Hopefully this language is useful to you as you start your journey in modeling. So I showed you a model of applications, and at some level you must be thinking, right, well, where's the software actually running, right? So let's start off with that. Here I've got a set of machines, and I just arbitrarily label two of them M1 small and two of them M2 large, whatever that means. And you can see Memcache running on one of them, HAProxy running on another, and Wikimedia and MySQL. So far, so obvious, right? I had that logical model of software, and then I've mapped it down to a set of machines running software. But I could actually, that same logical model could represent a slightly more complicated picture where I actually have HAProxy and Memcache both on two machines, with one being active, one being passive effectively. And MediaWiki spread across the 4 large machines, MySQL also on 2 of those machines. And you see how the logical model hasn't changed at all. I still have the same stuff connected to other stuff. I've just started to express more clearly. You can just start to see how the logical model and the physical model, the machines, relate to each other. So we're going to have to model machines in this story as well as the software running on those machines. And that's not super interesting. Where it gets interesting is when you start looking at something like this. This is a very simple OpenStack, right? This is only 16 odd services. And in this model behind there, it's modeled currently as mapping to 13 machines. It could get much more complex. I don't have a fancy software-defined network here. That could be another 5 or 6 services, right? Applications, effectively. I don't have complicated storage. I don't really have much, this is just the basics, right? 101, OpenStack 101. Now, mapping that to 250 machines, where different services might be either scale out and you want them on 200 machines, or not scale out, you want them just on 3 with provisions for HA. Oh, I also don't have any HA wrappers here, things like Coruscant Pacemaker or Keep Alive D or any of the other sorts of things you might wrap around these and model as well, right? So this is super simple. So let's dig in a little, right? Let's have a look and say, just that piece over there, that's Rabbit MQ. Now, Rabbit is used in lots of places, not just in OpenStack. So ideally, that should be a piece of Rabbit that I can use anywhere, not just in OpenStack, right? What would that look like? What would I have to do? Well, I'd have to have some way of saying, when Rabbit is around, there's a bunch of things that I'm going to need to do wherever Rabbit is going to be. And so this is what we call a charm. And a charm is a collection of scripts written in any language or sets of collections of languages using any tools, right? Ansible playbooks, Chef Solo, whatever DSL, whatever takes your fancy as to how to get stuff done with Rabbit. And we've got a bunch of raw materials. We may have some existing scripts or playbooks or stuff like that understands that particular app. And we may have a bunch of tarballs, zip files, things which are very specific to that application, which we like to get from particular places, which we're willing to share with a bunch of other people. We might have Ruby gems or NPM packages, PyPy packages, Golang builds, Docker images, stuff that essentially are the raw materials of getting Rabbit up and running in a really great way. And then we've got a bunch of things we need to get done. We need to install and remove that software. We've got to think about how we would handle scale out if that Rabbit was running over 2 machines or 3 machines or 4 machines. We've got to think about the modes of operation. Are we optimizing for resilience? Or are we optimizing for throughput? Or are we optimizing for footprint, right? You would lay that software down differently in those different high-level scenarios. We'll think about what we need to communicate to the outside world in terms of status. And we think about what we want to integrate with, right? This is Rabbit. It's fundamentally something that gets connected to other pieces of software. We want to think about that integration process. And we distill all of that down into this charm. So charms encapsulate as a series of scripts, which we call hooks, installation, configuration. We're still doing configuration management, but invisibly. We're doing it inside this charm. And we don't care if 2 different charms use 2 completely different tools, just like we don't care if 2 different apps are written in different languages, right? We're essentially encapsulating the operations of each application independently. Upgrades, updates, scale out, and even more interestingly, scale back, right? Health checks. Well, how do I know that Rabbit is healthy? What signals, what indicators should I emit? And in fact, all of these are lovely things to crowdsource because no one person, no one institution is going to do this perfectly the first time. And the more different people you have looking at this, the more efficient your implementation, the more secure your implementation. All the same benefits we get from the process of crowdsourcing and collaborating around packages of shared software. Operational actions and benchmarks. So what do charms do? Charms obviously include all of that knowledge, but they also declare interfaces. So here I've got a MySQL charm and a Wikimedia charm, and they each declare multiple interfaces which have names, right? So MySQL might have a dbslave interface. That means that it can be hooked up to another one of itself or something that speaks the same interface to be its slave, right? The MySQL interface, it provides MySQL. The syslog interface, that looks to me like some way to connect it up to something to do with logging, right? In fact, those are just names, just enforced by convention. It's a social community, just like the idea that if you apt-get Apache, you're not going to get Nginx, right? And the fact that those 2 charms declare that they have a common interface, MySQL there, and the one says that it provides that, the other says that it consumes us, is what allows us to say those 2 should be related. So we have charms, we have applications, we have interfaces, and now relations. So these 2 apps now have a MySQL relation. Now, when we do that, what happens? Well, there's software on both sides. And what we're asking to happen is that the software on both sides, which is doing the configuration management, not Juju, but the charm, which is doing the configuration management, handle some sort of conversation between those 2, some sort of message passing conversation, which does whatever it should do. And that's completely unspecified. It's going to vary depending on the interface. But typically, the person who wrote the MySQL interface will also write most of the code which can be professionally cargo culted into the other charm, right? To set up everything that's needed on the other side to have that relation to MySQL. So when those are related, those 2 sets of pieces of software essentially exchange messages. The messages are neutral to any format. On either side, they may use Chef or Puppet or Ansible or Python or Bash or Perl or whatever suits your fancy, right? You are essentially configuring 2 different pieces of software, and different communities are driving that independently. But through testing and convention, they work. Now that model scales really beautifully because we can now encapsulate and build communities around pieces which get better and better, and have interfaces which can be substituted. So this is how, over time, we get to deal with real complexity really elegantly, right? At first, this is a lot of work, right? Just to set up Wikimedia in MySQL. But over time, as the number of possibilities grows, it becomes possible to create richer and richer and more interesting topologies very, very quickly. Think how much more productive Debian developers are today than they were 15 years ago, because there is so much more there already to work with, right? That you can create faster and faster thanks to that existing set of capabilities. Okay, so digging into the model even further, an application these days doesn't just run in one place, right? A single application in the model, we call it MySQL, but actually it could be 2 machines or 3 machines or 4 machines collaborating together to provide that MySQL. And we call each of those machines, effectively, not the machines, each of those pieces of MySQL, we call those units. So you have applications and units. And of course, the same charm will be installed in each machine that's providing that application. And the charm will learn that it is one of 4 units or one of 2 units, or if it's the only unit. So the charm has to essentially deal with what goes on there. So we can think about MySQL units as having peers, the other MySQL units. And if they're related to something, then they have counterpart units on the other side. And if you really get into it, you're going to have to start figuring out in the charm all the interplay between those. So imagine, for example, I go and add another MediaWiki. What do I need to do? First, I need to tell the 4 existing MediaWikis about this new one. They may need to know that they got a friend, right? And I need to do something to figure out which database endpoint each of those MediaWikis is talking to. And you see that that's not a simplistically an everything talks to everything pattern. I might want to, for example, just pick on particular databases. There may be reasons why I would connect them up in a particular topology. Juju's not doing any of the configuration management. It's just providing this model for the underlying configuration management systems to do their work. Okay. Since we've got this great community that is knowing more and more about how you run MySQL at scale for highly resilient or highly available or very fast type deployments, right? We may as well gather everything we can learn together and everything we can collaborate together. So for example, how do I very efficiently back up the database, which sounds easy, but then you think I may need to schedule that to not impact the service levels that I'm providing. I may need to, for example, understand when I've got active and passive databases that I want to do the backup off the passive database, not off the active database. So in fact, things that are very easy to do straightforwardly become really hard to do brilliantly, amazingly. But through crowdsourcing and through open source, we can actually all be as good as Google, right? Because over time, that operational competence gets deeper and richer and better. So vacuuming databases, benchmarking, resetting logs, optimizing, those are the sorts of things you might expect to see as actions on a database. And in a content management system, you may flash caches, refresh content. These actions are completely specific to that application. They're not related to the model. They're just things that people can go in and do. But instead of SSHing there and doing something you know to do, this is now a system that declares a possibility to you, which you can take advantage of without having to go and get the book on that software. Okay. So one last thing on applications and units. It's a very useful construct sometimes quickly to be able to pick one. And often it doesn't matter which one. So Juju will designate leaders, right? It'll say this unit is the leader, and it'll switch that if that unit becomes non-responsive. This is super useful if you've ever done distributed systems development, because having some external mechanism to pick a leader saves you from having to do your own Raft or Paxos implementation, right? Unless you really want to write a compiler, right? Which you can do. But having this kind of scaffolding makes it much easier to operate in distributed systems. So this has to be completely cross-platform. And today, you can write charms on Ubuntu, CentOS, RHEL, and Windows, right? All of those platforms are supported. So you can weave topologies of software which include applications on different operating systems. And that gets kind of interesting when you think of mapping that to machines. So here again, we have those machines, but I'm going to call them the way we call them, machine 0, 1, 2, 3, 4, 5, right? We can do a really interesting thing these days with containers. We're interested here not in Docker-style application containers, but we're interested in LXC or LXD style machine containers, right? Just like virtual machines give you the feeling of a whole machine with all of the stuff running in the background that you want to have running in the background when you're running CentOS or Windows. A machine container is exactly the same. It's a container, but it's not like Docker. It's running all of the processes that you would expect, right? So we can create some machines running CentOS and Ubuntu, and then we can create a container on one of them. And so that was machine 3, so this is now machine 3/LXD/0, right? And that can be one of many containers. So I take my 6 machines, and I actually now create, what's that, another 7, so 13 machines effectively that I can deploy this software into. And since LXD is effectively a hypervisor, I can have CentOS on Ubuntu in a container or vice versa, no problem. So now all the software has to be mapped into that. How do we do that? Well, we can, for example, just put one piece of software on each machine. Now we know that those things aren't really going to tread on each other, but it's quite wasteful. We can also, if you look down here at machine number 1, I think, we can put Memcache on the same machine as HA proxy. And all that means is that the scripts from both of those charms are going to execute there. Now, of course, those 2 scripts could collide with each other. We take care to make sure that they don't run at the same time, but they might still overwrite the same files. So a better way to do this might be to put one of the pieces of software like that, MySQL, into a separate container. That lets me do it with a different Linux, effectively. But it also, if I don't want to do that, it also very efficiently, without any virtualization, lets me keep applications segregated from each other, but inside the same process space, inside the same machine or virtual machine, with no overhead for communications between them whatsoever. And lastly, remember, the charms can do whatever they like, including things like launch a KVM container. So we've got old software from the 80s that was running in like QNX or DOS, being driven by charms effectively because it just runs in KVM. And the modern way to do stuff like that is to use Docker containers. So charms can start Docker containers and Juju can track those. So here you have actually multiple Docker containers for those Memcache processes, and say I was using Docker to launch my MySQL as well. And what's interesting there is you've got everything in a modern container world, right? You've got machines or virtual machines, you've got process containers or application containers like Docker, and you've got machine containers or container machines like LXD, all on one picture, all in one model. Okay, we also have to model the landscape, right? So this is one of the things that we learned more recently, is that it wasn't enough for us just to model the application, just to model the software. We needed to model the world in which the software is going to run. And that's important because in order to let multiple people reuse the software, reuse the operations, we can't hard code anything into those operational pieces. Otherwise, you end up cutting and pasting the way you do today with playbooks or recipes, right? And cutting and pasting is profoundly unsatisfactory compared to the very passionate reuse that we get with real software. So since we can't modify those things to contextualize them, we have to be able to describe the world in which they're running efficiently enough that that stuff can get reused. So imagine a network. This could be a bunch of subnets on AWS. This could be a bunch of physical subnets. This could be a bunch of stuff in your own OpenStack or on VMware. It doesn't matter. What matters is that I have a sense that some parts of that network are the DMZ. And so I just group all of those subnets and call that the DMZ. And some other portion, some other collection of subnets is where I run apps. And then I've got a super secret secure portion behind a lot of firewalls and intrusion detection and deep packet inspection, and that's my PCI secure zone, right? That's where I store credit card details. And so what we can now do is we can now say, look, we're going to have machines that are in those different places, but we don't really want to worry about that. Really what we just want to do is say, stick HA proxy in the DMZ and stick MediaWiki and Memcache in the apps space and stick the database in the PCI secure space, right? So by modeling the network landscape effectively, we can get away from having to insert IP addresses or local network knowledge into the orchestration system or the configuration management system. We do a similar thing with storage, right? So we say you can declare different pools of storage that have different properties. And so, for example, on EC2, you could have fast EBS and slow EBS and ephemeral instance volumes. You could have TempFS. And you can implement that in lots of different ways on lots of different virtualization systems or clouds or bare metal. Doesn't really matter. But you call them storage pools. And then when you deploy your workloads, you can say where they should draw storage for their stores from. So for example, HA proxy, we run stateless. It doesn't have any stores. Memcache has a cache, but that cache effectively is stateless, right? It's ephemeral. It's just a cache. It might get quite big, but we can pull it from TempFS, then it'll be really, really fast and totally ephemeral, right? MediaWiki, well, that's going to have a directory somewhere with a bunch of files in it, a bunch of content. We don't care how fast that is, but we do care that it doesn't disappear, right? So we could use slow and cheap storage for that. So we said, do you deploy MediaWiki and map the content store to the slow pool of storage? And MySQL, we could say, oh, well, we've got the database and we've got a journal. And we could pull the slow and cheap storage for the database and the fast, expensive storage for the journal. So again, this MySQL charm with its different stores becomes completely reusable. I don't have to map them that way. We're separating out the modeling of the particular environment that you're running that stuff from the modeling of the application itself, so that when you deploy in production or when you deploy on your laptop for development or when you deploy into a cloud, you can essentially bind things very cleanly, very elegantly, very simply, and you're still reusing all the best practice. So that reuse is what's so powerful, right? We know that reuse drives quality. Very profoundly in software, reuse drives quality. It also drives features, right? Software that you use that's getting used by many, many other people is more likely to have a feature you're going to need, right? And it drives cost down dramatically, right? So reuse is good. We also often don't realize how many times we are redoing the same work. Think about your development environment. In many cases, that's a script that essentially assembles on a laptop or on a VM all the different constituent parts that you use in production. But it assembles them completely differently. Often they're all hooked up to the same IP address. Often they are essentially just Hulk smashed into the same image, right? Whereas in production, those pieces would be split out. And that causes all sorts of problems. We are constantly seeing bugs landing in OpenStack because developers of OpenStack are essentially running this distributed scale-out piece of software all in one process space, all on one IP address, right? So things which don't show up as bugs on a laptop easily make it into the code base and then have to be teased out when they go into production. Even CI systems often, for convenience, because we don't know how to reuse the production scripting efficiently, end up essentially allowing those bugs through. So today, you can benefit from reusing stuff cleanly across dev, test, and production. But there's a deeper benefit, which is once this stuff becomes reusable across communities, then you get the benefits of collaboration from outside your institution or outside your community. Okay, Think of how many times or how many different clouds you might deploy the same piece of software. A large organization today is deploying the same database in all of these places. Every major cloud, their private cloud, their old VMware, and every laptop, right? Every developer laptop. Similarly, that same database is showing up inside topologies from completely different teams. How many times do you want to have to solve an operational problem? Once. And so thinking about how to be smart about that kind of reuse is super useful. So here is a MongoDB. I can plug that into any topology which needs a MongoDB. But again, because it supports a standardized interface, I can also plug into all the same topologies this sharded cluster of 13 machines running MongoDB, and it takes me about the same amount of time, right? I can spin up a topology that has MongoDB, and if I like it, I can then spin up that same topology but substitute the Mongo single server for that cluster, and I now have a highly available, highly sharded, very scalable, seriously scalable MongoDB, right? That's stuff that will take many teams days or weeks, right? And having done it once, they're reluctant to touch it, right? Why they're reluctant to touch it? Because it was expensive, right? And it works, so don't touch it. But how do we learn? We learn by breaking things. And to break things, you have to be willing to do them again and again. It has to become cheap to redo something. If you really want to learn how software behaves at scale, you need to effectively make it cheap for yourself to throw it up, tear it down, throw it up, break it, right? Tear it down, throw it up, try to break it again. And this is what lets you do that. So here we are. This is an OpenStack. That's an OpenStack plus a Kubernetes. We are highly likely to see organizations starting to spin up multiple kinds of scale-out infrastructure, right? And those pieces of scale-out infrastructure are going to want to communicate, which means we're going to want to reuse pieces across them, right? We're going to want to spin up stuff on OpenStack and connect it to stuff that we're running on top of Kubernetes or Docker Swarm or Mesos or some other scale-out DOSCO, Docker-style container orchestration, right? And we're going to want to do the same thing with PaaSes. We can build these bigger and bigger combinations of scale-out infrastructures, and we need to glue those things together. To do that, we have to go beyond automation. What you do today is automation, and it's important, and it's good. But to get to this, to master this, to get to the next level, we have to go beyond automation. Think about this. When you are deploying something that wasn't written in-house and that is also being deployed elsewhere in the same building by other people and is also being deployed elsewhere in other buildings, you should stop doing configuration management, because you're spending time on something that fundamentally cannot be important to your goals, right? You should start doing configuration management as soon as you're in a place where the software you're working with is unique to your organization, right? Then it's all up to you. Then the only shoulders that can be there to tune and tweak and optimize and secure that software, but yours are the only shoulders that matter, right? To date, we haven't had the tools to do it, but with Juju, and I'm sure in time with other modeling systems, we will gain the ability to encapsulate the stuff you use today in its myriad and fanciful different forms into things that can be glued together much more usefully and much more powerfully. And I leave you with a thought. People love to talk about immutable infrastructure, right? But you understand that there's a trick at the heart of all of that, because every piece of immutable infrastructure was modified to become what it became, right? So the key question to be thinking about is, where was it modified to become what it became, right? We love to say, look, you can take a Docker container and then spin it up in many different places, and it's immutable, which is great. It's also a little prickly, because if you want to mutate it, well, it's immutable, right? So the key thing to start thinking about is, where was that thing born? And how do I essentially move that process to the place where I actually need it to be? You see, the immutability is super useful from a reasoning perspective, but it's super awkward from a life cycle perspective. And if we can bring these two ways of working together, I think you'll find life gets much better. We're building essentially apt-get for the cloud, apt-get for the cluster. And it's absolutely amazing. I hope to see some of you guys around and about this week. I want to finish off with just two things which are universally interesting, I think, and not specific to any one tool. The first is, will this work? Let's see if that works. The first is something called MAS. This is a rack of servers over here. I could pop the lid off and you'd see 11 little Intel NUCs inside. So there are actually 11 servers over there. And this is MAS, Metal as a Service. It's like a physical cloud. It will let me take a look at each of those nodes. Let me understand, for example, what fabrics it's attached to, what Ethernet devices are in there, what disks, and how they are partitioned. And it'll let me, for example, create RAID volumes or LVM volumes, divide up the partitions, and then deploy an operating system on there. So, for example, on this MAS over here, I think we currently have Ubuntu. So you can see there 15.10, 14.04, AMD 64, and CentOS 7, RHEL, and SUSE, custom images, and Hyper-V. So on this page, I could take a NUC. Wow, come back. Where are you? And I could say, right, let's deploy Trusty on that. You'll see there are the other operating systems, but let's just go ahead and deploy Trusty. And with a little bit of luck, you'll see a light coming on. And so we've powered on a machine. Imagine that's in your data center somewhere. We've powered that machine on, and we'll have Trusty on there in about 3 minutes, which is pretty fantastic. With the bonded NIC that you asked for, with the partitioning schema that you asked for, with the operating system that you asked for, all done. And so that gives me a nice language, an API, a REST API essentially to the whole data center, which is pretty fantastic. Well, what could I do with that? Well, here I have, no, not here I don't. Here I have a Juju model, a blank model that is connected to that MAS cluster. So I could go and say, well, let's put OpenStack on there. So I'm going to the clouds, and I'm going to use this one. So this purports to be OpenStack base. That's a picture that you might have seen earlier that says that it will give me a Liberty release of OpenStack. So I'm going to drop that on here. And again, with a little bit of luck, you'll see lights coming on, essentially machines that match the requirements for those different components of OpenStack are being fetched from the data center, turned on, operating systems are being installed on them, and then the charms are going onto those machines and installing all of the various pieces of OpenStack and command and control and connecting them up together. It takes about 15 minutes and we'll have an OpenStack up there. The second thing I wanted to show you is something called LexD. Now, you may have, who's used LexC? Okay, so LexD is basically LexC 2.0. It'll be in 16.04. The beta just landed at linuxcontainers.org, and it's pretty amazing. So, That's because I'm in, oh. This is never mind. So this is my laptop over here, and this is a cloud now with LexD Lexi. I can go and in about 1 second, I've launched Ubuntu. I can do it again, and it still takes about a second. So the reason this is interesting is because essentially that problem of having developers work on distributed software in a non-distributed way is solved in 1604 with this, because you can essentially use your laptop as a cloud. You can create as many containers, as many Linux containers as you like in all of the major flavors of Linux, and you can spin up all the software that you want in separate machines. Each of those gets its own IP address. Each of those is a full running machine effectively. And with something like Juju or Chef or Puppet, you can essentially orchestrate everything that you would run on the cloud in that machine. So this is a profoundly exciting time because we're putting distributed computing cheaply in the hands of every developer in the world, which is super exciting. So on that note, thank you very much. I hope that's useful, and have a very, very good 2 days and a great week. Two questions. Question up front here. Right, I've got it. I've got it. So this is a great question. The question is about security, right? I'm randomly pulling software from the cloud and running it in my data center. How do I know that it's safe? And I think it's a very profound question. It is, you know, the same question you get with Docker images and containers, right? Docker run today is semantically exactly the same as wget pipe to sudo bash, right? I think the really important thing is that because charms are typically open source and curated, there are many eyeballs looking at the same code for the charm. Second, because the operational logic is separated from the bits effectively, you can audit that operational logic. You can actually see what it's doing. It's exactly as if you could see the process by which a Docker container is getting created. See, when 3 or 4 charms land on a new container in the cloud, what's actually happening is that a pristine CentOS image or a pristine Ubuntu image is being started. And then these scripts which you can audit, or which at the very least go through a community process exactly the same as the community process that we use for packaging software in Ubuntu, right? And in Debian. Those scripts are then executed against that pristine image. So you don't have the same set of concerns. It is an interesting question, right? But today, when you apt-get install something, you're running scripts as root, right? So it is very, you know, morally equivalent. And I think the community process that underpins charming is crucial to getting this right. One more question.
Where all the come close it, James, you'll see it.
Come and see it. I think we have a booth, so you can come and see this in action on the booth. Right. So the question is, how do traditional operations expertise, or how does operational excellence in, for example, how you handle upgrades, how you handle cross grades or migrations, how does that play out in this world? And I think the crucial thing is that it happens iteratively, right? So the first version of a charm is inevitably good enough for whoever wrote it, right? If it's useful, if it's good enough for the next person, right? If it's a good enough starting point, it will grow whatever competence they bring. And so what we observe, which is really interesting, is that as a charm gets used in different organizations, they bring different competence to that process. You see the same charm go into a bank, and suddenly it gets key escrow wherever it had key gen, right? You see the same charm go into a telco, and suddenly it's got hardening of the security. It's interesting that the telcos care more about the security than the banks in many cases, right? You see the same charm go into a media organization, and what do you think happens? Huh? More scalable. That's exactly right. The media organizations, they run at very lean margins per gigabit of traffic, right? So they're super focused on how to do it efficiently. That same charm gets much better as it goes through more organizations. Nothing for nothing, right? The reality is it's software. It has to be written. It has bugs. It gets fixed. But here's the beautiful thing, right? By the time you get it, 99% of the time, it's already amazing, right? And that is something you can't say of from scratch operations. On that note, Chris, thank you very much. It was a pleasure to be here.
Thank you very much.